Hello dear students, welcome you all. Students, today we are going to start the unit number 4 of your course. This unit is based on Maxwell thermodynamic relations and their applications, right? So here in this unit, the first topic is thermodynamic potentials, right? So you know very well. We have already discussed it in the class also. Uh, so, so first of all, in this unit, the first topic is thermodynamic potentials, right? First of all, we will discuss thermodynamic potentials. Then, by using these thermodynamic potentials, we will derive Maxwell thermodynamic relations. These Maxwell thermodynamic relations are basically four Maxwell equations, which are very important in the statistical and thermodynamic course, right? So I'm coming to the first topic, that is thermodynamic potential, right? So you know very well, while we are dealing with a thermodynamic system, right? There are certain parameters which are very important for describing that system, right? So for example, let's consider we have a cylinder that is fitted with the piston, frictionless piston, right? Now the thermodynamic behavior of the gas contained in that cylinder can be described. We know the prominent three parameters, P, V, and T, right? Pressure, volume, and temperature. If we know any of these two variables, right, then the third one can be calculated by using the help with the help of equation of state, right? PV is equal to RT in the case of ideal gas, right? And in real gases case, this equation got modified. So by using the help of these equations, we can calculate, any unknown variable. But in this, these equations are limited. We know in reality, for the full description of the system, we need several functions like P, V, T, S, U, G, and H. Here, P, V, T are usually the three variable. S, entropy. U, internal energy. G, gives free energy, right? H, enthalpy, right? So here, of these U, G, and H, they have dimensions of energy. Now, in principle, we can have several functions of the thermodynamic state of the system, right? Which can be obtained by combining these different quantities. But only few of them are having physical significance, like Helmholtz free energy, Gibbs free energy, enthalpy, right? So we are going to consider only those, right? So here the important, you know, state functions of a thermodynamic system are internal energy, right? Enthalpy, right? Helmholtz free energy, right? And Gibbs free energy, right? Now we are going to discuss one by one, all of them. First of all, I am coming to the internal energy, right? So we know very well the internal energy of a thermodynamic system will be, if I write it by U, U will be equal to the sum of kinetic energy of gas molecules plus potential energy of gas molecules, right? Now, if we consider that the gas molecule do not interact with each other, right? So in that case, the potential energy will become zero. So the total internal energy of the gas will be equal to U kinetic energy, right? So this is the internal energy. Now, the second thermodynamic potential is enthalpy. Enthalpy is basically the total amount of heat content, right, in a thermodynamic system. Total amount of heat energy contained in a thermodynamic system is represented by enthalpy, right? And mathematically, H is equal to U plus PV, right? Similarly, the third thermodynamic potential is Helmholtz free energy, right? Mathematically, it is F is equal to U minus Ts, right? Now, Helmholtz free energy is basically a quantity that measure the useful work that is obtainable from a closed thermodynamic system at constant temperature, right? So here it is very important. The temperature is constant, means the process is isothermal. So Helmholtz energy tell us that how much amount of work can be obtained from a thermodynamic system when the system is under thermal equilibrium. Now the fourth one, that is Gibbs free energy or Gibbs energy, this is H minus Ts. Now again it represents the maximum amount of work done in a thermodynamic system when the temperature and pressure, now the two things, temperature and pressure, are kept constant. So these are the four important thermodynamic potentials which are very important for making the complete description of the thermodynamic system, right? These thermodynamic potentials play the same role as the potential play in case of mechanics, potentials play in case of electrodynamics, right? So you can say that these potentials are basically linked with the state of the system. They are responsible for any change in the thermodynamic system, right? So these are the four thermodynamic potentials, right? So it is interesting to mention here that U, H, F and H are collectively referred to as the thermodynamic potential or free energy that I told you. So of these, Helmholtz energy is particularly important as it provide a very important connection between the thermodynamics and statistical physics. Yes, statistical mechanics. You will learn all these things when you will proceed further in this chapter, that how it is important, right? Now we are going further and we are making the differential form of these thermodynamic potentials, these four thermodynamic potentials, right? So for that, I am coming to the first one, that is internal energy, right? So internal energy was U, right? U was internal energy. We know from the first law of thermodynamics, dq is equal to du plus p dv, or I can say du is equal to dq minus p dv, right? So if I put the value of dq according to second law of thermodynamics, dq is equal to tds. So it becomes du is equal to tds minus p dv. So it means change in the internal energy U is directly dependent on the change in entropy S and volume B. So we can say U is a function of direct function of S and B, right? And this is called the differential form of this first thermodynamic potential, right? Now I'm coming to the second one. Second one is your enthalpy. It is denoted by H, and H is equal to U plus PB. If I took the derivative, half derivative, dH is equal to du plus PdB plus BdP, right? Again, if I put the value of du here, du means T ds minus P dB. So PdV will get cancelled with the PdV. You will be left with the dH is equal to TdS plus BdP, right? So it means the change in enthalpy dH is directly dependent on S and P. So we can say H is a function of S comma P. Clear? So this equation is the differential form of your second thermodynamic potential. So the next one is Helmholtz free energy, right? F. F is defined as U minus Ts, right? So if I took the derivative, dF is equal to du minus T ds minus s dt, right? So if I put the value of du tds minus p dv, so tds will get cancelled with tds. You will get minus p dv minus s dt, right? df. So it is clear here that the change in the Helmholtz free energy is direct function of F is a direct function of B comma T, right? And this equation is the differential form of this thermodynamic potential, that is Helmholtz free energy, right? Now the last one, the last thermodynamic potential was Gibbs free energy G, and it was G was H minus Ts. Clear? The value of H was U plus P B minus Ts. So you got G is equal to U plus PV minus Ts, right? Now I am taking the derivative. dz is equal to du plus pdb plus bdp minus sdt minus tds. Clear? Du again it is what? tds minus pdb. So tds cancelled with TDS, PDV cancelled with PDV. So you are left with here B D P minus S D T. So it means the change in the Gibbs free energy dz is equal to B D P minus S D T. So it is dependent on the change in these two quantities. So we can say G is a function of P comma T, right? So these are the differential form of this equation, including this equation, the last equation that we derived here. These are the four equations, right? This is first, this is second, this is third, and this is fourth. These four equations are the differential forms of four thermodynamic potentials that we are going to use for the complete description of a thermodynamic system, right? Now, what is the utility of these thermodynamic potentials? What will be their significance? So, we must know what is the significance of these potentials and differential form of these potentials. We know a mechanical system is said to be in stable equilibrium if the potential energy of the system is a minimum. It is obvious, right? For example, in case of a thermodynamic system, heat flow from higher to lower temperature region till equilibrium is achieved. Here we are talking about the thermodynamic system, right? Also, water flow from higher to lower level to achieve minimum gravitational potential energy. And here in case of heat, this process takes place to achieve minimum thermodynamic energy, right? Heat flow from higher to lower temperature. So this is the analogy between these two. As U, H, F, and G are all energy functions in thermodynamics, so they behave in a similar way as the potential energy behave in case of mechanics. Here it is clear from this example, right? Here we have equated the gravitational potential energy with the thermodynamic potential energy, right? At the end of this chapter, you will see that in an isochoric and adiabatic process, the internal energy of the system will tends to remain minimum, right? Whereas in isobaric adiabatic process, the enthalpy tends to stay minimum, right? Similarly, in isochoric isothermal process, the Helmholtz free energy tends to get minimum, right? In isobaric and isothermal process gives free energy tends to attain minimum value, right? So this is the significance of these thermodynamic potential, how they are linked with the stability of the system, like in isochoric process, adiabatic process, isobaric process, and isothermal process. You know very well what are these different processes, right? Like isochoric is that process in which the volume, total volume of the system remain constant. Isobaric is that process in which the total pressure remain constant. Similarly, isothermal is that process in which the temperature of the system remain constant, and adiabatic process is that process in which all P, V, and T change, but there is no exchange of heat between the system and surrounding, right? So this is basically the significance of these thermodynamic potential, how they are linked with the stability of the system, right? So here we have discussed about these four thermodynamic potentials, that is internal energy, enthalpy, Helmholtz free energy, and Gibbs free energy. We saw how they are linked with the stability or any situation in a thermodynamic system, right? And these are the differential forms of these four thermodynamic potentials, right? Now in the next lecture we will use these four thermodynamic potentials with their differential forms for driving Maxwell thermodynamic relations, which are very important for for showing the behavior of a thermodynamic system, or explaining any thermodynamic process in detail, right? So this is all about the thermodynamic potentials, right? Thank you.